Okay, please go ahead.
Hello everyone. I hope you all can hear me well. First, I want to thank Behshad and Toronto Steely for providing this opportunity for me to talk to you guys. And as Behshad said, I am a Category 4 vibration analyst. Currently, I work in Saint Mary's Cement, which is a part of Votorantim Cimentos group. I'm going to talk about role of IoT and machine learning in predictive maintenance. And just to add, the reason that I'm talking about this subject is I worked in a company that makes wireless vibration monitoring platforms. So I was in that company for about 2 years. And before that, I completed my Master of Science in Mechanical Engineering, in which I was working on machine learning and developing machine learning models to diagnosing dynamical system faults. So this area has been my interest for a while. Okay. Let's review the agenda for today. First, I will talk very quickly about maintenance strategies, preventive, predictive, and prescriptive, to know the scope that we are talking about. Then I will focus on the main pillars or main ingredients of what called prescriptive maintenance, which are wireless sensors, connectivity, predictive and prescriptive analytics, and visualization. Then I will review a few challenges that we may encounter in this way of implementing prescriptive maintenance in an industrial environment. And at the end, we will have a question and answer. And just to mention that this session is a kind of awareness training. So the topics are wide, and we will have a chance to just walk through it and try to have a general understanding of the topic. I hope that in future I have some chance to like present other webinars with more details about any of these subtopics that may be of interest of you guys, so like machine learning or other stuff. So let's get started with maintenance strategies. Almost everyone knows that we have 3 main maintenance strategies: reactive maintenance, which means usually leave the equipment to fail and then fix them; preventive maintenance, which usually means planning and scheduling maintenance activities based on time. So this is very common in industry. Still, it is very common in industries, this type of activities. Then it comes to the next, which is predictive maintenance. This is mostly traditional condition monitoring solutions, like collecting vibration, oil, or temperature data and analyzing, and then diagnosing faults and taking action based on the faults that we have found. And it is pretty human-based. So, and it has been in place for, I guess, at least more than 50 years. So it has a kind of long history behind it, and it has well developed in different area of condition monitoring technologies. Then it has come to the next version of it. To me, it's not a totally different strategy as the previous 3 ones are. They are basically 3 different animals. But what is called prescriptive maintenance, I prefer to call it, let's say, a smart predictive maintenance or autonomous predictive maintenance or AI-enabled predictive maintenance, because it is basically the same predictive maintenance empowered with some, we will see, with some computer-based like intelligence, like machine learning, and also some infrastructures like IoT. So things are being done like by humans and also by machine in combination together. And this term prescriptive maintenance has come to like maintenance literature from data science literature, because they have predictive and prescriptive analytics. So yeah, whatever you name it, either prescriptive maintenance or smart predictive maintenance, it is based on four main pillars or ingredients. First is wireless sensors, then connectivity, which is kind of the infrastructure that uh, all of the topic or the area is based on that. And then some tools like predictive and preventive prescriptive analytics, and then visualization tools. So I will review these four pillars in this webinar, and to mention that there is a base for these four pillars, and it is named as cloud-based platform, which is a kind of internet-based servers that consist of database in which you store data, processing power, and UI or user interface or dashboard. Okay, the first pillar is wireless sensors. Wireless sensors are in use in different and many different applications. I guess you have heard of smart buildings, smart vehicles, smart transportation, I don't know, smart power transmission network, smart uh, transportation, fleets, anything else, and including our application, which is we call it prescriptive maintenance or smart predictive maintenance. So it's all about collecting data and transferring data in a new way. This is the theory behind wireless sensors. So how wireless sensors work in our context? Let's say it has three different steps, or it is comprised of three different steps. First is sensor itself. It can be a wireless vibration sensor, oil sensor, temperature sensor, or any different kind of sensor. I will talk about the sensor structure and what it is, what it is in the inside the sensor later. And there are some solutions that different kind of sensors can connect to a platform, like is shown in here at the bottom of the left side of my slide. And that let's call it a hub or whatever. And that hub acts like communicates with the second component, which is called as gateway. Or sometimes the sensors themselves communicate with the gateway. So different versions are available. This communication between sensor and gateway usually is done on using like Bluetooth, but it is possible to be done on other communication protocols as well. They have chosen Bluetooth because it is like a low power consumption method for communication. And gateway is a hub or electronic device that can communicate with sensor from one side, and also the cloud or the like dashboard or server or whatever you call it. Usually we call it cloud. And this communication between gateway and cloud is based on internet connection, and like wireless, regular wireless, or cellular data, or who knows, maybe in future some other technologies. So these are the main three ingredients of a wireless sensor platform. I need to mention if there are a few sensors in the market that they can act standalone and they do not need a second hardware as gateway. There are a few of them in the market, like these two guys, and they directly communicate to the cloud, to the server. And let me say, let's say by communicating, I mean they start sending data. And also they start receiving data and configuration. So this communication is a two-way communication. So what's inside a wireless sensor? A wireless sensor consists of four main elements, which are shown in this picture. Basically, they have a sensing element, which is traditionally our sensors, like what we know as a sensor is the sensing element mainly. Like a vibration piezoelectric sensor, I don't know, an oil particle sensor, a temperature sensor. Traditional sensors are mostly only the sensing elements, or or maybe very small electronic chip, but only a chip to uh, electronically condition the sensor output. That's it. But here, besides the sensing element, we have a main board, which is in fact a mini computer. So it is kind of programmable. It's not just a small chip that uh, like in piezoelectric sensors do some very brief voltage regulation. It's not just like that. It's a mini computer. It can be programmed. It can send data. It can receive data. And the way it communicates with other elements is an antenna, which can be different kind of antenna based on the need or application to be able to communicate with different under different protocols like Bluetooth or Wi-Fi or cellular data. And also it gets its power usually, or in most of the cases, from a battery. So the fourth element is a battery. Uh, I need to put a word here, different sensors, and this right picture is actually radiation sensor, but it doesn't matter. The sensing element can be anything. The two left pictures are two example of wireless vibration sensors, but they basically have these four elements. I just want to add a word about the battery. Be aware of that different situations is there for different brands. Some of them have rechargeable battery. You can recharge the battery after a while. Some of them have like just one-time use battery, which is replaceable. You can replace it. And some of them, even the replacement of battery is not possible, and you need to throw out the sensor after the battery is dead. So there are three different like battery management there. Be aware of this when you are choosing your sensor, vibration, or other monitoring sensors. And an interesting point is that number of available sensors in the market like has been increased by a factor of 3 or 4 since 2010 until now. So I myself was able to count more than 30 different brands of wireless vibration sensors. So that's a big number because this technology is a kind of new, but it is growing very fast, and you can see here and there different kind of and different brands of wireless sensors. Currently, mostly vibration sensors, but you can find other wireless sensors like for temperature, for process, for oil, for electrical parameters. Yeah, you can find almost anything because the point is any measurement element or any sensing element can be theoretically added to this platform of wireless sensor. So you can integrate any sensing element to the main board, antenna, and battery and make a wireless sensor for measuring almost any parameter that is measurable, like by traditional methods. So yeah, it's a very broad area. Uh, let's talk about where the wireless condition monitoring stands with regards to other traditional methods. Uh, in terms of measurement frequency and equipment criticality, we have online monitoring solutions which measure data in a real-time manner. They are almost wired. They are usually very, very expensive, and it can be vibration monitoring, temperature or thermography or thermal scanning or online monitoring of oil particles or viscosity or any different condition monitoring parameter. Because of the cost, usually this kind of monitoring is used for very high critical equipment, like the main equipment in a plant. On the other side of the spectrum, we have manual data collection, like regular vibration data collectors, thermography cameras, oil samplings, and sending samples to laboratories. Usually, we use this kind of data collection for balance of plant equipment. These are the traditional methods. Wireless platforms or wireless monitoring kind of stands in between. So you can usually wireless vibration monitoring is not recommended for very high critical machines, but anything other than that, balance of the plant equipment and other equipment can be can benefit from wireless monitoring. And in terms of even in terms of measurement frequency, it is something between like real time and manual data collection. And to add more, wireless monitoring is not supposed to replace any of these two left and right end of a spectrum. It is going to be added to the solution. So let's say we have three different solutions for our equipment to be monitored, and we can select any of them based on the situation. Uh, like where wireless condition monitoring can play a better role. Let's say for assets where there is a safety issue for manual data collection, like they are in a hazardous environment, there is heat, height, etc., or they are difficult to access because of they are in remote locations, space is very limited, compact. So in these cases, you can easily install a wireless sensor and start monitoring those assets, which usually are difficult or sometimes impossible to be monitored using traditional manual methods. And because of the cost, you cannot add wired or regular traditional online monitoring. So in these cases, wireless sensors are very important and can play a good role. Another benefit of wireless condition monitoring is when you need more frequent data collection without spending a lot of money, right? So in terms of wireless condition monitoring, collecting 4, 5, or 6 data per day is pretty common. Even you can collect more data. I will talk about that in the next slide. But the most common frequency of data collection is 4 or 5 times per day. And what limits us here is the battery. So because if you use the wireless sensor more frequently, the battery uh, like uh, will die sooner, and We will talk about this later in our last slide, which is about the challenges. Another advantage of wireless condition monitoring is there are pretty different kind of wireless sensors, so you can have integrated condition monitoring implemented based on this, and they are pretty easy to install. Let's say less than 10 minutes, you can install and configure a wireless sensor. It's a kind of plug and play sensor. Uh, And because of this and the cost, they are very easy to expand. So you can start in a pilot program, just for example, install 10 sensors. And if you are happy, you can expand it into, let's say, hundreds of sensors in a matter of day or I don't know, a day or two maximum. So it's this feature really is not possible with traditional wired monitoring system because they are very time consuming and difficult to install and wired and those stuff. But the wireless condition monitoring, believe me, you can easily expand them to any of your equipment that you want to do that. Just a point about continuous monitoring. If you want to uh, collect data more frequently, let's say every minute, there are a few brands in the market like Predictive 4 that because the battery is rechargeable and there is a port on the side of the sensor that you can connect it to the power source, like let's say charger. So and the like infrastructure of the sensor and the back end of it is capable of collecting data very frequently, let's say every minute. So even you can think of continuous monitoring, not real time as it is in wired sensors, but kind of uh, more frequent data collection using this sensor, or if there is another brand that I am not aware of that. So even this one is possible, continuous monitoring. Okay, that's enough for wireless, our first pillar. The next pillar is connectivity, thanks to Industrial Internet of Things or IoT. Uh, this context I have found in Wikipedia, and it describes the IoT concept very well. So I'm going to read it from here. It's a kind of complex technical topic, IoT. So the Industrial Internet of Things refers to interconnected sensors, instruments, and other devices networked together with computers, industrial applications, including manufacturing and energy management. This connectivity allows for data collection, exchange, and analysis, potentially facilitating improvement in productivity and efficiency as well as other economic benefits. The IIoT is an evolution of distributed control system or DCS that allows for a higher degree of automation by using cloud computing to refine and optimize the process controls. So as you can see, it covers all of the main pillars that I mentioned before. And IIoT concept is not just about condition monitoring or generally speaking monitoring. It is also about process and equipment control. So it's a wider area than what we are talking about. But as I said, it's connectivity, which is part of our pillars, is based on the uh, like the concept of IIoT. Even the wireless sensors, usually they are called as a IoT device as well. And maybe even IoT device is a better name because we call them wireless sensor, but you saw that they are pretty more than just a sensor. They have a mini computer inside of them. So maybe device is a better word to call them than like only sensor. And the IIoT platform consists of many different elements, including our sensors. It can be also actuators, controllers, some real-time control boards, some like human machine interaction, LCDs, edge gateway, internet, cloud, and other many stuff. Uh, what distinguishes between the network or the internet and the edge is the place they are. They are basically the same thing in different places. So the edge is a network that is placed near the sensor, usually in the site or in the plant itself. And some IoT platforms have the edge, some of them do not have. So that's not a mandatory thing. It depends on the application. Just let me review a kind of list of protocols and standards that are used for different part of IoT platform. For its infrastructure, we have IP version 4 and 6 and RPL and etc. For communication, we have Wi-Fi, Bluetooth, cellular, NFC, LoRa. For data protocols, we have MQTT, and some other stuff. For device management, we have TR-069 or OMA-DM. For security of data, we have OAuth, OTRP. So you can see that different component of an IoT platform has a lot of different standards and protocols that makes it a kind of complicated platform. And almost all of these stuff are a software like theory or software engineering knowledge. So I'm a mechanical engineering, but I just wanted to mention these names to you guys so you be aware of like technical terms that are used in an IoT topic. So let's get back to our application. How this concept helps us in implementing a condition monitoring program. So based on those stuff and the connectivity that provided by IoT, we can easily integrate our monitoring system to, let's say, for example, our CMMS, SAP or Maximo or etc. We can integrate it into our plant's control center, control and monitoring system, like what you have in your control room. And this can be, any of these integration can be a two-way communication. For example, if you are able to integrate your wireless monitoring to CMMS, you can initiate work orders from that side to CMMS or configure your sensors using your CMMS. So it's a two-way communication. And if you integrate it into your process control monitor and monitoring, you can uh, integrate condition data with process data and use, like, let's say, correlation analysis. And you can integrate those data and like use machine learning to diagnose the faults better. You can integrate your monitoring system to any local monitoring systems like HMIs or other local monitoring system, like very near to the equipment, or some complex machines that have their own interface like HMI. And also the concept of remote diagnostics. Uh, it is pretty common that you can give access to your dashboard or your wireless monitoring system, and other people anywhere around the world can help you diagnose your data, your faults, and monitor your machines. Let's continue with our third pillar, which is predictive and prescriptive analytics. So uh, if we want to talk like in order, the first thing that comes is a fault or anomaly or abnormality detection. As we are monitoring our equipment, first we will notice that something is wrong. That we call it fault detection or anomaly detection. Then we need to make a fault diagnosis. Here we call it automatic fault diagnosis. It can be based on expert system or AI-enabled diagnostics. Uh, both of them are computer and like program based, like I mean computer program based. The main difference is expert system are rule based models. Like let's say for example, in terms of vibration, this can be a rule. If vibration is high on one times machine speed and it's higher on, let's say, radial than axial, and then if the machine is in between bearing, then, for example, the fault is unbalanced. This is just a very, very simple example of how expert system work. There are a couple of commercial expert system, for example, Expert Alert, if you have heard of it, from Azima DLI, that has consisted of 1,000 rules, like 1,000 rules that combine together to derive that expert system. Uh, this system is passive. It cannot learn by itself. It is already programmed to do the diagnosis. But on the other side, we have AI-enabled diagnostics, which is mostly based on machine learning methodologies. I will talk about this with more details later. So machine learning computer codes, they are capable of learning new things based on the data that we feed to them. So they are expandable. Uh, like in contrast to expert systems, which are usually passive systems, machine learning systems are active and they can learn and expand their knowledge. Then the next topic here is prognostic or remaining useful life prediction. Still, we can do this based using machine learning. Another application in machine learning, we call it regression. Uh, So prognostic is a kind of predicting the future of your parameter by forecasting how it is doing and how it can do in future based on the past data. This can be used for maintenance planning and how much lead time you have before the machine fails, for example. So it's Uh, in terms of application or applicability, the prognostic is much newer and still a work in progress, I guess. Maybe there you cannot find that much implementation of prognostics in commercial products, but fault diagnosis, there are some commercial products that have this feature already. And based on all these three elements, we can have an automatic alert system. Uh, Most of the wireless condition monitoring platforms have this feature. It's a system that sends email or short message or other ways of communication or using other ways of communications, and it will send a message to you if something bad is happening. For example, if an alarm or a warning is like exceeded, vibration is high or temperature is high, and if the system is equipped with the fault diagnosis, it also provides you with details about what is the fault and what you can do to resolve it. So let's talk a little bit more about machine learning and how it can be used in our context. So machine learning is a computer uh, like application that has different methods and has different like application like classification, regression, and clustering. Classification and regression are known as supervised learning because we provide input and output data to develop these two like as application of machine learning. And clustering is called unsupervised because we only provide input, not output. Uh, Let me explain a little bit more any of these three applications, so you know more about them. What we call classification, which is a kind of supervised learning, is like this. You have your machine learning model developed. Uh, First, you provide some input data which are labeled. For example, these shapes are fed into the model, and the model knows that, for example, I mean, we have provided that information to the model. That, for example, this shape is a circle, this shape is a hexagon, this shape is a triangle. So we feed data plus labels or tags or whatever you call them to the machine learning model. Then it starts learning. How it learns, it tries to find the features that make difference between these shapes. For example, I don't know, this circle has a round edge. This has a, I don't know. These are called features, and the machine learning model will recognize all of those shapes based on the features, uh, and it will be trained. So after this training part is done, if you feed new data without label, just the shape itself to the machine learning model, it will recognize that, okay, this shape is triangle and this shape is circle. So this is a simple uh, an easy to understand explanation about how classification works. Let me put it in our context. For example, you have your machine learning model, you provide it with vibration data, but that vibration data is labeled. It has a tag. For example, this signal is for a machine that is unbalanced. This signal is for a machine that is misaligned. This signal is for a machine that has bearing defect, etc. So data plus label or tag. So machine will start learning uh, to how distinguish between these three, for example that I mentioned. And after that, that learning or training phase will take time, sometimes very long time. It depends on the depth of the machine learning model. So after that learning or training phase is done, then you can send new vibration data that you do not know. Either it is unbalanced, misalignment, or bad bearing. You do not know. You have only the vibration signal. You feed that vibration signal to the machine learning model, and it will let you know that the fault is unbalance, misalignment, or bad bearing. So it's a pretty good and very uh, helpful feature that we can use in our daily deals with machines and machine condition data. The next application of machine learning is called clustering. Maybe clustering is not that much common in condition monitoring, or maybe it is. Definitely, it is less common than classification. Classification is used for fault diagnosis. Clustering can be used as a sort of preparing things for classification. For example, in clustering, you have your data, in this example, the shapes, but you do not have the name for them, the tag or label for them. They are just the shapes. And a different machine learning model will try to put them in similar groups. For example, it can recognize that, okay, these shapes are similar to each other. The second shapes are similar, the second group are similar to each other, and the same for the third. But it doesn't know, and it will not provide you with any label. So you need to name this any of these three categories. So how it can help in machine condition monitoring? I assume that sometimes you have a lot of data, but you do not know which fault they represent. So you can develop a clustering machine learning model, and you can put your data into it, and at least it will cluster them, or it will categorize them, so you can then manually see the data that are similar to each other. We are supposed that at that level they are similar to each other. So you can use the output to uh, uh, then you will have similar data, and it may make more sense to you that okay, this seems to be that fault, this seems to be this fault. Yeah, this is something that we can like take benefit out of this clustering. But as I said, the main ingredient of automatic fault diagnosis is called classification, not clustering. And the third application of machine learning here that applies to us is called regression. It is used for prediction of the future or forecasting. How it can help us? Okay, you have some machine parameters that you are monitoring it, and it can start rising, or it can start increasing. Uh, this this picture, the blue shaded area is past data that we have. We have measured it. Then that machine learning model can start learning the pattern based on the past data, and it can predict how the future will be or could be. So this yellow area is predicted. So based on based on whatever your parameter you are putting into context in this model like regression, it can be fault level, like how bad the machine is, something that represent the failure. I mean, the not functional and not let's say a fault that is progressing, not breakdown. So a fault that is progressing, or a condition that represent that fault. It depends. So for example, it can be vibration data, or it can be I don't know, if something is measurable directly. Let's say, for example, a bad bearing, you can measure the depth of the fault. Maybe that's not a good example because practically we cannot do that. But if it is possible that you can directly measure some aspect of the fault, like the depth of the fault for a bad bearing, for a spall, then you can predict how it is going to uh, get worse in future. I mean, any parameter can be that we have past data of it can be predicted the way it will or would react in future. Uh, Before I leave this third pillar, I would like to talk about one of the best machine learning methods, which is known as neural network. And the beauty of neural networks is that there are many different let's say architects, or the way that we can implement them. You know, the basic concept is the same. Any circle, any of these circles are called cell, uh, like similar to our neurons in our brain, and they are connected. They can be connected to each other in a very different ways, and every like let's say vertical set of these cells is called a layer. For example, this model that currently I'm showing has 1, 2, 3, 4, 5, 6, 7, 8 layers, and it has a lot of cells, right? So based on combinations that you can make out of these cells and number of them and different cells, some of them are input, output, memory, and different kind of cells, and number of layers, and how they are connected to each other, like our brain, I don't know, something like that. You can make different versions of neural networks, and each of them is suitable for like a specific application. let's say, for example, image processing, video processing, speech processing. And in our case, let's say, for example, vibration signal processing, oil data analysis processing, oil data processing, temperature processing. I personally have used this deep convolutional network for diagnosing faults in bearings, and believe me, it has acted very, very well. I was able to diagnose bearing data with more than like 98% accuracy. So this technology is very promising, and I'm pretty sure that currently they are still working on it. There are some commercial products that already have machine learning like used in them, but still it is a work in progress. I'm pretty sure that in maybe near future you will hear more and more about these applications. And let's put all of these things together in a fellow. So first we collect a lot of data from different sensors. Then we can do different kind of processing. Let's say, for example, if it is vibration, we can do FFT, we can do envelope detection, we can do wavelet analysis, and a lot of other like advanced signal processings. The next step usually is called feature extraction. Thousands of features can be extracted out of the signal or its converted versions like FFT, and those features will be fed into the like machine learning model. If you see this first layer, which is called input, this input is, for example, the features. The features that we extracted or we have found from our vibration signal. And those features goes through all of these layers, and then this last layer is output. For example, these features are like this vibration frequency, vibration amplitude for a particular fault, of course, for example, for an unbalance. And then the system will learn, will be trained, and this output will be, okay, machine is unbalanced, something like that, simply said. Then we can use those features and those machine learning models that I explained for health assessment, which is fault detection, for prognostic, prediction the future, for fault diagnosis, which fault it is. And the beauty of this convolutional neural network that I used it in my project is you even do not need to extract features. You can feed the raw signal directly to the model. And this is very interesting because if you get involved in machine learning, you will see sometimes finding the right feature is not that much easy. But the beauty of neural networks is that they can directly get the raw input data without any processing as input, and they can process them themselves. This section of the, like in pink, they can extract the features themselves. So I hope that we can get a chance to dig more deeper about this machine learning later. I just wanted in this session to just talk a little bit about it to make to spread awareness if you are not already aware of these technologies. Okay, our last pillar is illustration. So let me first show you this picture that shows how illustration can help us get like meaning and insightful meaning from out of our data. So as you can see, data can be these like Lego stuff. When you sort them at step 2, they look a little bit meaningful. And when you arrange them and present them visually, uh, even they will be more meaningful. But if you are able to explain what is behind them or what can be made out of them, definitely you will see the difference between number one and number five. So number one is a lot of data that we gathered out of our sensors, a lot of vibration signals, etc. And number five is when you have diagnosed the fault. Like let's say, for example, your machine learning model has diagnosed the fault. But before that, number three and four are how data can be presented in different shapes that can lead us to the diagnostic or correct diagnosis, or can pave the way towards that. So this part number three and four are called data science, and there are a lot of tools and technologies in data science to present data to illustrate the data content. And number six is the action that you need to take to resolve the problem. So we call it actionable insight. So if the machine is unbalanced, for example, maybe one solution is to balance it or to wash the impeller or whatever. So uh, and when it comes to data visualization, this is where our wireless vibration monitoring or wireless connection monitoring communicates with the users. We called it a dashboard. It is called a dashboard. So it can consist of a lot of different visualization tools. Let's say, I don't know, a sketch of the machine or a photo of machine, pie charts, bar charts, tables, trend lines, and believe me, a lot of other tools and technologies that are used to demonstrate data, to visualize data, and regular stuff. Let's say, for example, vibration spectrum, FFT, waveform, thermography images, so plenty of other stuffs. So this is the last layer of the wireless platform, which is sometimes we call it user interface or UI. And simply said, it's a dashboard. It's a cloud-based dashboard. It's a software that is installed on the servers, not in your local machine, for example, similar to other Windows software. But it's not like that. It is installed on the server, and it can be customized and used in control room. Like a simple version of it is suitable for operators. It can be customized for reliability and condition monitoring engineers, usually with more details. It can be customized for maintenance shop and technicians and millwrights. It can be customized for plant and maintenance managers. So this this possibility to customize the dashboard is a very important advantage of it that can make it suitable for different group of users. And as I said before, it can be accessed from any kind of device, let's say your phone, your tablet, your laptop, anywhere that is able to connect to internet and have a screen, you can have access to this dashboard. Okay, let's wrap up our talks with a quick review of challenges that we may encounter in this way. Currently, the two main challenges are battery life first, and then availability of internet access, which is either Wi-Fi or mobile data. So battery life, still, I can say still is a major issue, even though they have, I mean, the providers, they have tried to increase the battery life. Believe me, they are working because I used to work in that similar company. They are working on power consumption of hardware, like in terms of microamperes, very like accurate measurement of battery consumption, and they are trying to optimize it to increase the battery life. And on other sides, you know, the battery technology is always evolving, newer batteries with higher capacity and longer life. But anyway, anyway, it's a battery, right? And it will drain and it will die at some point. So that's an issue still. Then you will need either Wi-Fi or a mobile network to send data into the internet. And if for any reason neither of these two is available, then you cannot implement that wireless monitoring system. The good news is that at least mobile data is almost available everywhere. So maybe there are some solutions to help us when where that mobile data even is not available. I don't know, it's a kind of communication technology, but I think there are some solutions to cover those areas that mobile data even is not available. For example, by installing some antenna or some tools. Another challenge is data security because we are talking of internet and all of the data will be available online. But the good news is that as secure as your bank account is, so these systems can be or are the same secure as that. So they are providing a very secure protocols, like to name a few, auth protocol. So your data usually will be secure, but be aware of this. So when you are talking to your provider or you are like investigating the potential providers, you need to make sure that the security is good enough. Another issue or challenge is uh, do we have a single platform, integrated platform that covers all of the monitoring parameters that we need, or we have about different, let's say, for example, our vibration wireless is from a provider, our oil is from another provider, I don't know. Are we have, do we have data islands or we have an integrated platform? So that's another challenge that you may encounter. So there are some providers that that make a different kind of sensors at the same time. So that's the advantage of those providers. And thanks to the protocols and standards, it is always possible to like integrate different providers to each other. As I mentioned a few names in terms of protocols. For example, there is a concept named as API communication. So even if you buy different things from different providers, sometimes it is possible to integrate them together. They can communicate to each other and send data to like each other, like the platforms that they have. And the last thing is if the hardware is HAZLOC certified, it is suitable to be used in hazardous environment or not. That's another story. So thank you very much. We are running out of time. Uh, now we have a question and answer session, so back to you, Behshad.
Thank you, Hussein. It
You're
was a
very
great
welcome.
presentation, starting from the basic to the end. I really appreciate that. Couple of
You're welcome.
questions. I think you address one of them in your challenge slide. It says, is cloud basic concern with respect to opening up a production control system to internet terrorism or something like a data security that you mentioned? So, do you have any
Yeah, yeah.
comment on that?
I know that as I just named a few, there are very secure protocols to avoid this, to like keep your data safe. But even when these protocols enhance, the like hackers or I don't know, the competitors, they also enhance their system to attack you. So it's a kind of game that is in progress. So you need to always enhance your security based on the latest developments. That can be a challenge, I guess, for not for all of the industries, maybe for very like for industries that the security is a big problem.
Yep.
And another thing, if you remember, I mentioned something as edge. So the edge technology is a kind of servers that can be installed in your plants. and can carry most of the load of data and everything. So edge solution can be, or sometimes they call it on-premise servers. So those two concepts can help those industries that need more secure data, more secure place for their data other than regular cloud-based internet like those provided by Google or Amazon.
Perfect.
So those local-based solutions are kind of more secure.
Perfect. Thanks. Another question that I have is there like a temperature range, cold and hot for these sensors, for the oil, for the vibration? They work at -40 or something like that, or no?
Yeah, definitely. Each sensor has its own data sheet. You can always review it or ask the provider to let you know. Uh, I know that they are pretty good at low temperatures like -30, -40, and high temperatures like like 50. So, but it's not maybe the case for all of the sensor. I can suggest review the data sheets or ask the provider. And keep in mind that the wireless sensor or wireless device is similar to other devices. It has battery, it has electronic boards, it has sensing elements. So any of these can be sensitive to low or high temperature. So, but providers design it in a way and make it in a way that can tolerate those harsh environments.
Okay.
And speaking of this, let me mention that IP level, there are a lot of devices that come in very high IP levels, like 67, 68, or there are some devices that are already certified for being used in like a hazardous environment, like
Mhm.
that explosion proof and those stuff. So yeah, all of these areas are already covered by the manufacturers of these monitoring systems.
Okay, so the last question that I have, and if there are any other question, people can type or unmute themselves, is I think somewhere in your presentation you mentioned that for the critical equipment or element, you don't use the vibration sensors. Did I hear it right?
Uh,
Or
no, not, I mentioned that usually it's maybe my personal recommendation. Usually, wireless monitoring platforms are not recommended for very high critical equipment because they are based on battery, they are based on availability of Wi-Fi, and these are not something that we can guarantee they are always there. So critical equipment usually need something that is highly reliable, like
mm,
a reliable power source, like regular power, not battery, and high reliable data communication methods like wired.
mhm.
So usually we cannot put our protection and our critical monitoring load on wireless like platforms. And it's not just about vibration, it can be about any parameter. Yeah.
Okay, thank you very much. So I don't have any other questions on the chat. If anybody else has any question, please unmute. I just want to thank you on behalf of Stili Toronto chapter uh, to give us the time for this great presentation. If anybody asks for a copy of your presentation and to be in contact with you, is it okay to share with them your contact information, Hossein?
Yeah, that's pretty fine. I would be happy to hear from any of the audience, and I also appreciate this opportunity. And I would like to thank you, Behshad, and Toronto Steely, and all of the our listeners. Thank you very
Oh,
much.
thank you very much. Okay, that would conclude today's webinar. Thank you very much, everybody. I will send a notice regarding the next webinar next week, which will be in April. Thank you, everybody, and have a great day. Bye now.